Radius of convergence and interval of convergence. Here's an example. Find the radius of convergence and the interval of convergence for this series, this power series. Sigma x minus 2 raised to the n minus 1 over n going from 1 to infinity. This is a series, an infinite series, power series because there's the variable x raised to powers. We typically find both of these, radius of convergence and interval of convergence, using the ratio test. According to the ratio test, in order for a series to converge, we need the limit of the n plus first term over the nth term, and we're going to use absolute value, so we'll have absolute convergence. We need the limit of this ratio as n approaches infinity to be less than 1, because if the limit of this ratio is more than 1, then we would have divergence. If the limit of this ratio is 1 exactly, then the ratio test is inconclusive. Limit as n approaches infinity. A sub n in this example is this with n plus 1 in place of n. A sub n is going to be x minus 2 raised to the, instead of n minus 1, it's going to be n plus 1 minus 1. And denominator instead of n is going to be n plus 1. A sub n plus 1 means replace any n, that's here and here, with n plus 1. The n plus first term of this series is x minus 2 raised to the n over n plus 1. Because right here, n plus 1 minus 1 is just n. That's the n plus first term. Over the nth term is just what has the blue circle around it. X minus 2 to the n minus 1 over n. Absolute value. We need the limit of this ratio, the blue to the green, as n approaches infinity to be less than 1 in order for there to be convergence. Limit n approaching infinity. We're going to change this division of the blue divided by the green. We're going to change it to the blue times the reciprocal of the green. We still have the absolute value. We still have the is less than 1. Limit as n approaches infinity. X minus 2 to this exponent over x minus 2 to this exponent is just x minus 2. Because when dividing with like bases, x minus 2 is the like base. We keep the base, x minus 2, and subtract the exponents. The exponent up there minus the exponent down here is 1. We still have this green n in the numerator and this blue n plus 1 in the denominator. I'm going to erase this. This is my subtracting these exponents. Make sure you see that that's just 1. Well, since n is approaching infinity, the absolute value of x minus 2 is sort of like a constant, at least in this limit situation. So we're going to bring that with its absolute value to the left of the limit. X minus 2 is over here. Since n is approaching infinity, the limit has no effect on this. That's why I shoved it out there. So the absolute value of x minus 2 times the limit as n approaches infinity. Since n is approaching positive infinity, we don't really need these absolute values here. And n over n plus 1 is the same as 1 over 1 plus 1 over n. Dividing each term by the highest power of n. And this is 1. Just bringing that down. And the rest. The limit of this as n approaches infinity is 1. Well, now we have an inequality, an absolute value inequality. The absolute value of x minus 2 is less than 1, which means the x minus 2, the thing inside the absolute value, has to be between negative 1 and 1. And we add 2 over here, bring this down, add 2 in this middle section, bring that down, add 2. 1 plus 2 is 3. And now we actually have to test the endpoints, the 1 and the 3. When x is this endpoint, this is what the series looks like. Sigma. I'm just going to replace every x with 1 in the original series way up here. The series with the blue around it. I'm going to replace the x right here with 1. And then in a little while we'll replace x with 3. So the series when x is 1 is 1 minus 2 to the n minus 1 over n. Which is 1 minus 2 is negative 1. So that's negative 1 raised to the n minus 1 times 1 over n, and starting at 1 and going to infinity. You hopefully recognize that this is the alternating harmonic series. Alternating because of the negative 1 raised to the n minus 1 times this harmonic part. So it's the alternating harmonic series, which converges. We discussed this in a previous video. The alternating harmonic series is an alternating series that converges. You should look back and see how we proved that it does using the alternating series test. So what we do is we go back up here. When we had x's between 1 and 3, we now know that when x is 1, like there was x, this is a series that converges. So 1, underline this, is part of the interval of convergence. Now we have to check out 3. When x is 3, back to the original series, replace x with 3. Right there is where the x was. It was x minus 2 to the n minus 1 over n. And going from 1 to infinity. Well, 3 minus 2 is 1. 3 minus 2 is 1. 1 to any exponent is 1. So this exponent disappears. 3 minus 2 is 1. 1 to the anything is just 1, always. And we recognize that this is the harmonic series. This is the famous harmonic series, which famously diverges. The harmonic series diverges. As we saw in a previous video. We can also prove that it diverges with either the integral test or the p-series test. Harmonic series diverges. That means 3 is not part of the interval of convergence. We have divergence when x is 3. So this is the interval of convergence. It could also be written like this. 1 to 3, including 1. 3 is not part of it. The radius of convergence, so look at a number line that, and look at the interval that goes from 1 and goes up to 3. We can include 1, but not the 3. The distance between these two numbers on the number line is 2. And the radius of convergence is the distance from the exact middle of the interval to either endpoint. So we'd say the radius of convergence is 1. The entire width of the interval is 2. Half of that is called the radius of convergence. If you think of this distance as a diameter, and the radius is half of that. And we're going to do one more example. The question is to find the radius of convergence and the interval of convergence for the series, the power series, sigma x over 5 raised to the nth power and starting at 0 and going to infinity. X over 5 to the 0 power is 1. X over 5 to the first power is x over 5. X over 5 to the second power is x squared over 25, etc. This is a power series because it has powers of x. But this is different from the last one in that this one is geometric because there's a common ratio. This is a geometric series which only converges, geometric series only converge if the absolute value of r is less than 1. The absolute value of r cannot be 1, it cannot be 1 exactly, or greater than 1. So in this case, the r, the common ratio, is x over 5, because we're multiplying any term by x over 5 to get the next term. The absolute value of r has to be less than 1. That means the thing inside the absolute value has to be between negative 1 and 1. Multiply each term by 5. And there you have the interval of convergence. And the nice thing about geometric is we do not have to check the endpoints. Because when x is 5, we're going to have a geometric series that diverges. And the same when x is negative 5. We'll have a geometric series that diverges. So no need to check for those. The interval of convergence could also be written like this. Not including negative 5, not including 5. On a number line, the distance from negative 5 up to positive 5, that total distance there is 10. So the radius of convergence is 5. It's the distance from the middle of the interval to either endpoint.